Hello, class. So one of the things I wanted to do today was take you back to POE. Unfortunately, well, I wouldn't say unfortunately, but I do have quite a handful of students that have never taken POE. So this next section is going to be a little difficult without this precursor. For those that have taken POE, this is hopefully a good refresher. So the first thing I'm going to ask everyone to do is the following: grab a pen, a calculator or pencil, a calculator, and a piece of paper. It could be a scratch piece of paper, but one of the things I want you to do is the following. I want you to look at problem one and then followed by problem two on the next slide. These are available on your Google slide. If you go to the very first two slides of 322 on the Google slide, goal is the following. If you can tell me what the reaction forces are at A and B without just taking a guess, which some of you can probably look at it and intuitively get a pretty good idea, but can you tell me what the reaction forces are at A and B and show me mathematically what those reactions are? Not the guessing, but the actual mathematical proof of it. Same with question two. Can you look at points A and D, which we're going to assume that they were on two pin supports or that there was just no lateral load, so it was pin and roller. So we already drew the reaction forces. Can you tell me what R1 and R2 are? If you are confused at this point or have no idea, then this video is for you. So my very first question to start the day is, what is the reaction force at A and B on problem one, A and D on problem two? Take a moment now, pause the video, try to see if you can solve it, but otherwise, once you're done, come back and see if you worked it out the same way I did. I'm going to go through some background concepts to start, and then I'm going to work out this problem. All right. So why don't I minimize the screen for the time being, push it off to the side, and then go through a couple things. Again, this is a precursor to 322, but I am going to reference a couple things. Okay. This is going to be about static equilibrium. So what does static equilibrium tell us? Well, the very foundation of it is the following. And again, this is all stuff we learned in POE. Static equilibrium tells us that all the forces acting upon an object are counteracted so that the object remains stationary. So if something is deemed to be static, it means that not only the forces applied to it, so the loads on it, but also the reaction of the supports on it balance themselves out so that they equal zero. So that it doesn't move, right? In order for a beam, it has to be in static equilibrium to appropriately carry the loads. So one of the things that's really important, obviously, in structural engineering to go about static equilibrium. I don't know why this arrow is off, but one of the things that you should be aware of is that wherever a beam is supported through something like a column, then the columns are going to create reaction forces. The load that's applied to it, as well as the reaction forces that are counteracting that applied load, are said to be vectors because they have both a magnitude, which is something like 100 newtons, 100 pounds, but they also have equally a counter vector, a counter reaction force, which is considered a vector. All right. I'll get back to this in the next video. Something you should also be aware of is the following. Dependent on the type of support you have, so now I'm going to draw a little bigger here. Depending on the type of support you have, whether you have something like a roller or pin support, you're going to get different types of reaction forces. So what do I mean by that? If you have something like a roller that's supporting the beam, it means that it's locked in here, meaning it won't allow it to push any further down, but it does allow the beam to slide left or right freely. So there's no force that's stopping it from moving left and right. So what's the reaction? Zero. The reaction in the x direction is equal to zero. However, if there's a downwards force, you better believe that this support here is going to act in a counter reaction force. So we can say that there is a reaction support in the y direction. Now, opposed to a pin, which is something like this. Oh gosh, we just draw them like this, and I can show you examples of them if we have time, but this video is probably going to go pretty long. It tells us that this is going to actually restrict it from moving because it's pinned here, so it's going to restrict it from moving this direction. So there is a reactionary force. So let's say someone pushes in this direction, there's going to be a reaction force in this direction. If someone pushes down, there's going to be a reaction force in this direction. So we have these two arrows. However, the reason why you're going to see the difference between pin connection and fixed supports is the fact that because this is a pin, it's like an axle. Just imagine that you have like a C channel connected to an axle. It's not going to move, but what it does allow it to do is to rotate. So there's no reaction force. These are the main two we're going to focus on. So I'm going to kind of whiz by the other ones. Just realize that for something like a fixed support, you also get a reactionary moment because if this object wants to rotate up, we'll say, the wall will prevent it and create a counter moment that will stop it from moving at all. It would be bad if it could rotate, right? I mean, it's fixed. There's other types of other terminologies that we might use. The most common we're going to say is simply supported. However, you should be aware that continuous beam support. So simply supported just means it's supported on each end. If it's continuous, it means it's supported intermittently as well. And then if it's cantilevered support, it means that it's only fixed on one end. There's other types, but I'm just going to move on from those. If it ever asks you to draw a free body diagram, you pay attention to what type of support it is, and then you draw the arrows. Inherently, we're going to always assume it's into the beam. However, that may not be true. It depends on the load conditions. The other thing to realize is that if there's no lateral force being a left and right force, we can assume that, I mean, we could prove it mathematically, but just to kind of move forward, we know that the horizontal reaction force is going to be 0 because it's kind of like saying, what's the force of me right now on my hands, or what's my reaction to the force? Well, there is no force, so I have no reaction. But if I go ahead and push on my hand, if I wanted to keep my hand in place, then I'm going to push back, right? So now we're fighting each other. But what's the reaction? Nothing. There's nothing pushing on me. So these are 3 static equilibrium equations. These are going to be really important to note. So some of the forces in the y direction equals 0, some of the forces in the x equals 0, and the sum of the moments equals 0. Before we move forward, I think it's really important to understand what moment is. So again, this is where POE would have helped you. But moment, very similar to torque, which some of you are familiar with coming into it, even without POE, but moment is the tendency of an object to want to rotate. So when a force is applied to a member, any object really, it creates a perpendicular. When the force is applied perpendicularly, I should say that, because if I just push in this direction, I don't cause a moment. Or if I push down on this object, one of the things that happens is I create a tendency for this pen to want to rotate, especially when I'm holding it on one end, right? Now this object wants to spin or spin. It doesn't do that if I just push it, inwards, right? However, what the moment formula tells us is that the magnitude of moment is equal to the magnitude of the force, so how hard am I pushing, times the distance, but perpendicular distance. So you'll realize I create like a 90, right? The perpendicular distance to what we call a fulcrum point, which is our point of rotation. Where would it rotate if it were free to rotate? So right now, these fingers are the fulcrum. When I push on this, it wants to rotate about that. So what would be the moment? It'd be the force, the magnitude of force times whatever the distance is from here to where I applied the force itself. All right, let's go back to this problem. Let's see how that helps us. So I'll do problem 1 with you guys. Hopefully you guys will solve problem 2 from there. I'm going to move fairly quickly through this, or else this video is going to be like 30 minutes long, but treat this as a lecture. I am going to extend this lesson because of that. So one of the things we're going to do is the following. I'm going to first draw the beam. And because it's got little wheels on it, we know it's a pin support. So I'm going to block it a little bit, but hopefully it's for the best. And then I have a 800 pounds And then I have 1,600 pounds. Okay, and then what is this? 30 inches. What an odd unit. I just got this off the internet, so actually I haven't solved this yet, so hopefully I get it right. Be bad if I made a video and got it wrong. Oh, see, I'm not keeping consistent. And then 30 inches. Okay. So first of all, you're going to want to draw a free body diagram. What does that mean? Well, shed these and then draw the reaction forces. So instead of redrawing it and wasting time on the video, I know that this is going to create an up and a right force. Technically, I don't know that it's up or right. It might be down somehow, but I'm going to assume this. The calculations will tell me whether I'm right or not. This is a roller support. We know that roller supports only create one reaction, specifically perpendicular to the beam direction. So I'm going to draw this up. I'm going to label this as R-A-Y, Ray, and this is going to be Rax. For some of you, or you might remember Rax and Ray, and then we got Ruby here. So Rax, Ruby, and Ray are going to join us once again. All right, now that I've drawn this, I can go ahead and expand on this a little more. Okay. So what am I going to do? Well, first I'm going to start by writing my formulas. Static equilibrium formulas, that's what we call them. Static equilibrium equations. I said formulas, but static equilibrium equations is technically how we call it. I accidentally wrote an F there. That's an M about a point equals 0. All right, now we go ahead and just, well, this is a free body diagram. I always like to suggest to people, I always circle my X forces. I always box my Y's. All right, well, this makes it pretty straightforward. It tells me that Rax, so again, sum of the forces in the X equals 0. There's only one, so we know Rax is going to equal 0, which technically I said earlier already. Now I'm going to move on to Fy. So sum of the forces in the Y direction. If it's pointing up, I'm going to assume it's positive. If it's pointing down, I'm going to assume it's negative. So I have a negative 800 pounds minus 1,600 pounds. Now all I'm doing is I'm, again, summing all the Y forces, all my boxes, plus Ray plus Ruby equals 0. Sum of forces in the Y equals 0. Then that's going to tell me that, so 0, I'm going to put it on this side, is equal to negative 2,400 pounds plus Ray plus Ruby. If I move it to the other side, it tells me, Ray plus Ruby equals 2,400 pounds. Now someone will incorrectly assume that this means that each of these is 1,200. It's not going to be. I've done enough of these problems to know that that's not the case. Well, I can't solve this. Why? Because I have two unknowns and only one equation. We have to create a system of equations. So that's where this third one comes into play. So hopefully this is where the whole right-hand rule will come into play. I always remember the right-hand rule. Sometimes I forget whether counterclockwise or clockwise is positive or negative, and I don't want to take guesses. So why don't we pin it about a point? So the formula says the moment about a point is equal to 0. Well, what point do we want to pick? Well, actually, I could pick either one of these, either A or B. So I'm going to pin it about A. And again, what I'm going to do is I'm going to take the moment created by each of these forces. So if I have a pen and I now pin it here, and I'm kind of blocking it, but if I push up, will that create a turning moment? No, it's just going to push my nail. It's not going to make the pen rotate. If I push in this direction, which I know is 0, but just for point, will this want to rotate? No, it's not creating a moment. It's just creating a reaction force, right? But if I push here, it wants to rotate. If I push here, or whoops, let me line it up. If I push here, it wants to rotate. And if I push here, it wants to rotate. See how it creates creating a movement, right? So the right-hand rule tells me that you put your wrist at the pin location, and then you just curl your fingers in the direction of the force. And then if your thumb's pointing away from you or into the paper, it means it's a negative force. Negative force. Then I have to flip my hand. The only reasonable way to do this is to flip my hand. Positive force. And my thumb's pointing towards me. So I'm always positive. That's not really true, but that's my saying, right? So that means that I have negative 800 pounds times the distance from this point to this point. Because again, it's a perpendicular distance, and that's 30 inches. Such odd units. Times, or sorry, technically I'm going to say minus because I know this is going to be a minus again. 1,600 pounds times, what's the distance here? 30 plus 90, sorry, 30 plus 60 is 90 inches. Plus RBY times 120 inches. And that whole thing's an equal 0, right? So little math calculations here. I know that technically I probably shouldn't even do this with the calculator. It's straightforward enough, but I know negative 24,000 pounds inch minus that one I do have to do because I don't know what those two numbers are. 144. Yep. Let me double check my values. 800 times 30. Yeah. 144,000 pounds inch plus, what is that? 120 inch RBY equals 0. I sum those two up and I move them to the right. I'm going to get 120 RBY equals 168,000 pounds inch. There's inches here. I divide by 120 inch, divide by 120 inch, and I get RBY is equal to, moment of truth, 1,400 pounds. Inches reduced to 0, or to 1. So RBY equals 1,400, which tells me that this right here is 1,400 pounds, which tells me that if I plug this back into here, that our AY has to equal, well, 1,400 plus what equals 2,400. Our AY had to be, oh, geez, I'm not even showing you guys. So I know this is 1,400. If I take this number and plug it right back into this equation, it tells me that RAY has to be 1,000 pounds. Very messy, but those are my answers. I'll box them. Ray equals 1,000. Ruby is equal to 1,400 pounds. They're both pointing up, and that's my answer. Now, what I want you to do is the following. I want you to go ahead and solve number 2 on your own. I'm not going to go ahead and show my work. Instead, I'm going to ask you to go ahead and solve it. I'm going to pause this video now, and then I'm going to come back with my answer. All right? I say I'm going to pause it, but I have to remember how to do that. All right, well, welcome back. Hopefully you got this answer that Rudy on the next problem for problem number 2. Hopefully you got it too, that Rudy, which is our DY here. I just called them Rudy. Rudy equals 800 and Ray equals 600. So on this side, we had 600 pounds of kilograms of reaction force up. This one was 800 kilograms of reaction force in the positive direction. If you got it right, you're ready to move on to this problem because you really got to understand these concepts in order to understand how we're going to use them now to determine what beam we're going to use. So if you still need more help, make sure to ask me during office hours. But otherwise, I'll see you guys tomorrow. Thanks so much for watching.